Welcome back to another lesson in which we explore yet another approach that will help us find digits of pi far past the decimal point. We've already seen how this can be done using geometry and trigonometry. We integrated various functions numerically and used that area to estimate pi. We also used a root-finding algorithm to estimate pi. Those were more visually intuitive ways of doing it. At least I think so. Next, we are going to explore infinite series. This will lead us to some of the most efficient algorithms once used to calculate pi to many digits. We'll start with this infinite series. The sum of the reciprocal of every odd term equals pi over 4. Notice that every other term is negative, so it alternates, positive and negative, positive and negative. This will be important very soon. The sigma notation for the same series is displayed in the second line. Notice that this series continues forever. We have to add an infinite number of terms to converge on pi over 4. Here I have made a spreadsheet. The third column represents the individual terms, 1 over 1, 1 over 3, 1 over 5, etc., etc. Every other term is negative. The fourth column is the sum of all the individual terms up to that point. Remember that this sum converges to pi over 4 when n goes to infinity. So to get pi, we must multiply that sum by 4. That is seen in the last column. Notice after 12 terms, we haven't even converged to 3.1. The entire spreadsheet is too long to display on the screen, so here I've scrolled to the bottom. After 500 terms, our approximation is 3.14, so we have 2 digits past the decimal. Infinity is a long way past 500. This doesn't seem to be going very quickly. Is there a better way? You may have noticed that the sum gets bigger then smaller, a little bigger then a little smaller again. Visually, that looks like this for the first 25 terms. Notice the red line these sums oscillate about. That red line equals pi. Do you think we could get closer to that red line by averaging the peaks and troughs? Numerically, that's exactly what I've done here. The number boxed in purple is the average of the numbers boxed in blue. Every other number in the last column is calculated in a similar manner. After 16 terms, n equals 16, we have converged to 3.14, with rounding of course. Already this is much better. Graphically, that looks like this. Notice the oscillations are much smaller than they were before. The blue line gets very close to the red one. If we were to continue this pattern plotted on the same scale, the two lines would be difficult to distinguish. Nevertheless, peaks and troughs still exist. They are simply smaller than before. If I average those numbers, our approximation converges to 3.141 after 16 terms. So basically I took the average of the averages. What happens if we take a third average? Our approximation to pi gets even better. 4 digits past the decimal, with rounding of course. As before, the number in purple is the average of the two values boxed in blue. After 4 averages, we have pi approximated to 5 digits of accuracy. It looks like we improve by about 1 digit of accuracy every time I take an average, at least for n equals 16. What happens at n equals 100? The entire table is too long to display here. This is just the end of it. Notice I don't need to take the average of every single row. That's why I get the triangle shape in the last 8 columns. This plays into the computational efficiency of the overall algorithm. The fewer calculations the computer has to make, the faster and more efficient it will be. Although the reason this works is different, the implementation is reminiscent of Romberg integration with its triangular shape in the table. That's just a side note. Don't worry if you're unfamiliar with Romberg integration. If you're curious to learn more, however, feel free to check out my previous lessons on that topic. Here I have zoomed in a bit. At n equals 100, we get 14 digits of accuracy after 8 averages. More or less, it looks like each time we take an average, the accuracy increases by 2 digits. As in previous lessons, we have reached the limits of this software in terms of how many digits it can store. Adding up the total number of calculations in this triangular region of the table, I get 36. Averaging involves one operation of addition and one of division. So we have done 72 mathematical operations. That increased our accuracy to 14 digits past the decimal place. Each new row in the original table involves one division operation and a summation. So an extra 72 mathematical operations would put us at n equals 136. In this row, our approximation to pi is not even 2 digits past the decimal. I'd say our effort was better invested in taking averages, as seen on the previous slide. That was just a teaser. Stay tuned for the next lessons. We will uncover where this infinite series comes from. If you enjoyed this lesson, I kindly ask that you share it with a friend you think could benefit from the information. Also, I'd greatly appreciate your feedback in the form of likes, comments, and subscriptions. Otherwise, thank you for watching. I look forward to seeing you next time.